Let's look at this circuit with a whole bunch of resistors in it. Okay, so we talked earlier about how to combine capacitors in parallel and series. We have similar ways of combining resistors, except for basically it's just the opposite. So resistors in series, they just add up. R1 plus R2 plus R3. So many. But now parallel is the hard one, the 1 over one. So 1 over R1 plus 1 over R2 plus 1 over R3, so forth. All right, so just the opposite of what capacitors were. Capacitors in parallel added up, capacitors in series were the hard ones. Okay, so remember, series means like a chain of people linking hands together, all going in a row. If one opens the one opens the connection, the whole path is broken. You can't follow through, right? Whereas parallel means it's like a ladder, and everybody's left hands are touching each other's left hands, and everybody's right hands are touching each other's right hands, and they're all locked together in a big kind of chain, a big set of things that are both touching both sides. All right, so it's looking at this circuit. Can we see anything that's in series or in parallel? All right, and one of the things with these is to think of the connections, these electrical wires, as being kind of like Play-Doh. They're flexible, they're stretchable. You can change them. It doesn't matter the shape of the circuit, doesn't matter the shape of how things are of the way they're drawn. What matters is what's connected to what, right? And so let's do a little practice on this one, redrawing it maybe a couple times to see what happens here. So looking at the circuit, can we see any that are in series, right? So that if the current flows through one, it has to flow through the other, right? Because series shares the same current. And so hopefully we can see that R5 and R7 are in series, right? Because any current that flows here has no choice, can't turn off anywhere, has to go down this road to the R7 as well, right? No offshoots, right? Any of these other ones, which one might, it might look like R1 and R6 are in series, but they're not, because current coming through R1, some of it could go to R5, some could go to R6, some could go to, so it has many choices, so they're not in series. I guess two other things that are in series is the voltage source is in series with R1, right? Because any current coming through the voltage source has to also go through R1. So those two are in series, but we wouldn't combine a source. Anyway, when we're doing these combinations, we're combining like things. We're combining all the just resistors. How about parallel? Do we see any that are in parallel? So studying it, parallel means if one end is connected, then the other two ends are also connected. That makes them in parallel. So looking at this point, there are lots of things connected, right? 1, 2, 4, 6, 5 are all connected here. But when we look at the other ends, one connects over here, doesn't connect directly to R2. So to be counted in parallel, they have to directly connect, right? Same thing, R2 and R4 are not in parallel because R3 is in between. But R4 and R6 are in parallel because the only thing in between is wire, right? So we could re-stretch or, adjust the shape of this so that it looks like more traditional parallel kind of things. And again, R5 and none of these are in parallel either because R7 is in between. So, but one thing that hopefully you'll get good at noticing, if we combine R5 and R7 in series and make them one resistor, then that one resistor would be in parallel with R6 and in parallel with R4, right? Because this end is touching and these ends are touching. Okay, so let's redraw this a little bit more, maybe in a little more easy form to see what's going on. All right, so I want to highlight the fact that these two are in series. I want to highlight the fact that these two are in parallel. 4 and 6 are in parallel, where these are in series. And that combination is also in parallel with these, which is in series with R3. So let's go ahead and let's kind of start over on this side of the circuit. So we've got R5 and R7 are in series, right? So if this was point, we'll call it A, right? So this is also point A, right? So here it was kind of stretched out in the corner. Here it's straight, doesn't matter. We're just connecting R5 to R7, all right? What happens from there? We're going to have, say, come over here and go to this point. Just call this point B. So that would be here. And then this point, maybe we'll call it C, is here. All right, so start at B, go to R5, go to A, Yes. Start at A, go to R7, come to C. Good. Okay. Now let's put in R6 and R4. Notice R6 starts at B and goes to C. So does R4. Starts at B, goes to C, right? It comes through here, but it all is just wire. So all of this is the same point. Doesn't matter how much wire. It's still the same point. Still just point C. So we can just do, how do we want to do this? We can do it like this to start with. Okay, so R6 and R4 are in parallel with each other. This is how we tend to draw a parallel, and they're connected to B and C, right? And so hopefully you can kind of see that they are also in parallel with this combination. If this became one, then that would be, the tops would be touching, the bottoms would be touching, right? A, B, and C. Okay, so let's come over, let's call this point D, I guess, and this point E. All right, so how do we want to draw this? Let's go ahead and put the label over there. And let's make this come down and make D be down here. And so then this is R3, because R3 is connected between C and D. R3, C to D, right? And if B, kind of just extend this top branch over, B is going to be connected to D through R2, right? So we can go like this. And it's good to kind of put dots where wires are actually connecting, because sometimes you have to make wires jump over each other. We might make a little jump kind of symbol, but it's good to try to be clear. So this one then is R2. It's connected, R2 connects from B to D. So R2 here is, this whole big thing is B now. We've stretched out B to make it a big point. And then this bottom is D. So R2 is between B and D. How about R1? R1 goes from B. So it's going to connect here somewhere. It's going to go to E. We'll just call this E. And so this is R1. And then we've got D and E, top and bottom, and that's where the source connects, right? The source is between D and E. E on the positive, long bar is positive, and negative on the D. Lots of times in electrical engineering, we'll call these connecting points, we'll call it a node, right? So node E. So I've changed the shapes of the nodes, but I haven't changed the circuit. So this circuit and this circuit, they're the same circuit, right? They're exactly the same. They might look quite a bit different. I guess I can write 12 volts here, and the current coming out of the source, we call that I. But we've still got the source in series with R1, R5 and R7 are in series with each other. R6 and R4 are in parallel with each other. Anyway, we've carefully put it back together piece by piece, made this one look a little square, where this one is triangles. We could make them all round and curvy or what have you. It doesn't matter the shape of the wires, it just is what's connected to what. Okay, so now if we want to get our total, maybe this picture makes it easier. And so we would leave the source, it stays the same, but we're going to just replace all those resistors with just one resistor, our total, that if we kind of look inside the box here versus inside the box here or here, looking at points basically E and D, the source wouldn't know the difference between all these resistors being there or just one resistor being there. All right, it's going to take the same current, going to take the same power, it's going to act the same. Okay, we'll call this I. So how can we find our total? Well, we can do a bunch of series of reductions and do it step by step, which is not a bad thing, but I'll probably do that way, drawing it with different colors of pencils. But let's do something here. So our total equals what? And so I kind of like to start on the inside. So we've got R5 in series with R7. Series resistors just add together. So we're going to have R5 plus R7. All right, that's going to be this. And so let's just replace it with one resistor like that. This is R5 plus R7. If we do that, then these are gone, and we've just got this. And so that's what this is, R5 plus R7, right? So now that R5 plus R7 resistor is in parallel with R4 and R6. So do we see that? And so for now we're just going to write parallel with these two parallel lines. All right, go back to regular pencil. So R5 plus R7, that's a series combination of two resistors. We made it as one. That combination now, I think this is gone, is in parallel with R4, and which is in parallel with R6. R6. All right, so all three of those are in parallel with each other. So if we want to write the equation for that, we would do something like this. But for now, we're kind of using the shorthand with the parallel stuff. Okay, so what would happen if I made all those into one resistor now? So all of these, right, R4, R5, R4, R6, R5, R7, all become one. So we could just replace that with one, this turquoisey resistor. Let's just call it RX because I'm getting too many names here. So RX is this, right? RX is R5 plus R7 in parallel with R4 in parallel with R6. All right, so it's going to be 1 over R5 plus R7 plus 1 over R4 plus 1 over R6. If we want to put in values, we could put in numbers and get a number for Rx. All right, so though this would be Rx, so looking at this Rx then, what can we notice about how Rx connects to the stuff we have left? So we've taken all these four, scrunched them into one resistor, calling it Rx, but now that Rx goes from B to C directly, and there's no other things connected to C, and so it continues on to D. So that Rx is in series with R3. Right? Rx in series with R3. Hopefully you see that. So if we kind of put square brackets around this, this is Rx. It's in series. When we add resistors in the series, you just add. So we're going to say plus R3. All right, what does that do? That makes all of this, these two, become just one new resistor right here. We could call that RY maybe. All right, because we combine the bluish green one with this R3. Now we've got RY here. It's connected between B and D like those two in series were. So it's now replacing those, and that's what this whole thing is. Maybe we'll put it in curly brackets. All right, that whole thing is RY. I guess it's easy enough to write as R3 plus RX. Okay, so if you want to, you can break it down piece by piece, redraw the circuit, and calculate these numbers by numbers. Or we're building up this big equation here, and we can just plug everything in a minute. All right, so now we've got RY here. How does that relate to R1 and R2? They're the only other ones left, right? Well, hopefully we can see RY connects up here at B, and then it comes next down here at D, which is the same thing that R2 does. So they are in parallel because they have both ends connecting. These two ends are touching and these two ends are touching. All right, so that whole thing, running out of room, is in parallel with R2. Okay, so this is RY in parallel with R2. All right, so then again, that is, I'm going to pull out a marker, I guess. Now we're going to combine those two in parallel, so then we're going to end up with a new resistance. Maybe we can call this RZ, right? And RZ is just RY in parallel with R2, which is 1 over RY plus 1 over R2. All right, if we had numbers, we've been calculating all these numbers, we could just plug it in, get RZ as a number if we wanted to. All right, we're getting there. So now we've got this new RZ, our old R1 still there, and the source is still there. So what happens now? These are all gone because they've been equivalenced. So now R1 is in series with RZ, right? So for series combination, I wish, anyway, I've got my lines here. But series just adds them up. So we're going to put plus R1. All right, so all of this is RZ, and it's in series with R1, so we just add R1 to it. All right, so this is the whole equation for R total. If we wanted to do it all kind of at once, it's a bit of a mess because of all these parallels in there, but we can write it like this. Okay, let's see, do we want to put in some numbers? Let's just put in some numbers just to get it, and how would be the easiest? Let's go ahead and calculate. So let's just do it like this. Say R1 is 1 ohm, R2 is 2 ohms, just to make our pattern nice and easy. R3 is 3 ohms, R4 is 4 ohms, R5 is 5 ohms. How many do I have? R6, 6 ohms, R7, 7 ohms. Okay, so R5 plus R7 yeah, let's just do it in some pieces because it's such a mess here with this parallel stuff here. So let's calculate Rx first. Rx was, we're combining these two in series first and then that in parallel. So Rx is kind of the first parallel combination. So it's R5 plus R7. R5 was 5. So it's 1 over 5 plus 7 plus 1 over R4 was 4 and R6 was 6. All right, so 1 over 12 plus get us a little bit of room here. So that was RZ. But putting in the numbers there, so in calculator we just do 1 divided by, make sure you put parentheses, and then 1 divided by, I'm just going to do it in my head, 12 plus 1 divided by 4 plus 1 divided by 6. And so the calculator knows the order of operations, and so it's going to do the dividing before it does the adding, so you can just kind of type that all in, close parentheses, enter, and so it shows it nice 1 over stuff. And what, anyway, all that comes out to be 2. Well, that's nice. Okay. 2 ohms. So Rx is 2 ohms. And so all of these 4, when we combine them into this turquoise thing, it just becomes a 2. All right. Let's go ahead and draw the circuit again with just that part, just so that it's clear. So we've got R1, R2, and now Rx is this, and then R3 is still here. So Rx equals 2 ohms, R3 is 3 ohms, so forth. Okay. R2, 2 ohms, R1, 1 ohm. Okay, so we said that, like we said, Ry is those two in series, and then we're going to get that whole thing in series. These two in series, if we combine them into one, that's in parallel with R2, right? That was RZ. So let's go ahead and calculate RZ, right? Because we've got, oh, well, what is RY? RY is just these two added together. So RY is just R3 plus RX, so it's just going to be 5. So we can just, let's write it here. So R3 is 1 over RY, which is R3 plus R5, R3 plus RX, plus 1 over R2, 1 over 2. So it's 1 over, X was 2, and 3 is 3. So 1 over, I guess we can write it 3 plus 2 plus 1 over 2. 1 divided by, in parentheses, 1 divided by 5 plus 1 divided by 2. Okay. 1.429 or 10/7, whichever one we want to write there. But anyway, RZ, 1.429 ohms. Remember, units for resistance is ohms. All right, so finally we've got RZ. That was RZ. All right, so RZ is now RZ. What was this? This was R2. Okay, so RZ is everything but R1, right? All these things except for R1. So R total then is just R1 plus RZ because they're in series with each other. So R1 is 1 ohm plus 1.429 ohms for RZ. So R total is 2.4, let's say 2.43 ohms. Okay, so big complicated mess. Just gonna look for, find something. Hopefully there's something in series with something or something in parallel with something that you can start combining. We could have combined these two in parallel first and then put those two in series and then combine that combination in parallel and gone from there. But just look for combinations. Redrawing is a good idea, maybe a couple times, so you can see what you need to do to get R total. All right, so we got the first one. What is the power absorbed? Okay, so which one do we want to do? Do I squared R's, V squared over R's for all of these, or just do it for the equivalent? I vote let's do it for the equivalent. So remember, we got PIV, P equals IV. We also have V equals IR. We also have VER. So VER, put that in there. That's how we get I times IR. So we get I squared R. Actually, I don't want to use that one because we don't know I, but we do know V. We've got the voltage, the 12-volt source now is right across. It has plus minus, and that's the same. Its plus is at E, which is also the plus, or it's also one side of R total, and the minus is at D, I guess that is, and that's on the other side of R as well. So the voltage across the resistor and the voltage across the capacitor are the same. So let's not do that version. Let's do, rearranging this, it says I is V over R. So we get V over R times V. So that's how we get the V squared over R. And so now we've got, let's use V squared over R total. So we've got V is 12, so we've got 12 squared over R total, 2.43, I guess we'll keep it extra sig fig while we're doing the calculation, 429 ohms, volts squared. All right, so we got 12 squared divided by 2.429, 59.28. I guess that's what was the unit. So 59.3. What's the units of power? Watts. Joules per second, but we'll go with watts. Okay. So this is the power absorbed. Resistors absorb power. Sources produce power. And it needs to be balanced. So if the resistor absorbed 59.3 watts, the source must have produced 59.3 watts because they're the only two things in the circuit, right? And so what gets produced has to be used up instantaneously. That's how the power system works. Whenever we turn our lights on, the power company generates the power we need instantaneously like that, and so it all matches up. It's all balanced. It's a conservation of energy kind of thing. Okay, so that was part B. Part C, I. What is I? All right, so we've got I here. Same kind of argument. We've got the voltage, we've got the resistance, and so we know VER, right? Or we know this, we can use this version of VER, I equals V over R. And so, again, I'd rather use this one resistor than try to figure it out with all this bunch, and that's kind of a good reason to make all this combination is so we can do some calculations. So voltage is 12 volts, resistance is 2.429, keeping 4 sig figs, so 12 divided by 2.429 is 4.94 amps. Thanks to VER. Okay, so that's the current in the source, right? It's current coming out of the source, feeding in the equivalent circuit, R total, feeding over here, feeding everything, but we can see that it, like I said before, R1 is in series with the source, so it is also the current in R1. All right, so that's what D is asking for. Well, we can use that for D. So what is the power in R1? Well, so we know all the resistors are taking 59, but each one is going to take a little chunk of that, right? And so each one is going to take, we can do V squared over R, I squared R, IV to figure out how much power each one takes, but we've got to know basically either it's voltage or it's current or both. So for most of these, we don't know voltage or current, but for R1, since it's in series with I, things in series with the source, things in series have the same current. So we know that we can use, we know I, so P for R1 is I squared R1, I squared R1, and we just got I, 4.94 squared times R1, which was 1 ohm. Okay, this is amps. Everything in the right units, so 4.94 squared is times 1 is 24.4 watts. Wow, it's got a bunch of them. 24.4 watts. So PR1 or R1 is using up quite a bit of the power of the whole combination, right? because it's getting the whole source current, right? It's getting fed a lot. Oh, we're running out of room. Okay, so we got I, we did that, we got that. Now we need, okay, it's gonna be a little trickier. R2. So going back to our circuit, one of the circuits, we can look at this one. We've got R2 here. We've got all these other resistors and stuff in parallel with it. The current I goes here, but it's going to split into two different currents. So I is not the current in R2. The voltage, 12 volts, is here, but it's not the voltage across R2 because some of the voltage is going to be here. Call it maybe V1, and some of the voltage is going to be here, V2. Oh, so now what do we do? Well, we're going to ask Ver for some help. Okay, where can I do this? I guess I'm gonna just make a little working box in here. Sorry for the messiness, but I don't want to flip the page because we'll lose our picture. So, if we knew V1, we know the total voltage from this bottom to this corner is 12 volts. We can see that V2 and V1, they add up to make 12. All right, so we can say V1 plus V2 equals 12. If we knew V1, then we could get V2, right? So V2 then would be 12 minus V1. And then if we know V2, we can do V squared over R to get the power in R2. That's kind of where we're going here. And so, what is V1? Can we get V1? Yes, because we know R1 and we know the current in R1. So this is going to be 12 minus I R1, right? Ver. V1 equals I R1. So this equals 12 minus I, 4.94, times R1, which is 1 ohm. So V2, 12 minus 4.94 times 1, 7.06 volts. Okay, so that's the voltage on R2. And so now we can use a different version of the power equation, different version of PIV with R. So these I squared R things only work if you have a resistor, right? If you have some other element, you have a source, it has no R, so then you can't use the R versions. But since we're dealing with a resistor here, we can use V squared over R version. And we're talking about 2, so let's do V2 squared over R2. We just figured out V2 is 7.06 squared divided by R2, which was 2 ohms. All right, so 7.06 squared divided by 2. Wow. 24.9 watts, even more. Sorry for the smallness here. 24.9 watts is PR2. Okay, So again, we've got 49 watts of the 59 is just in these two resistors. The other ones, when they get to be parallel series, they're going to share more power, and so all the power and all the rest of them would add up, and the total, if we add all of them up, should still be 59.3. So again, these two are taking a lot because they have the higher voltage and the higher current. Okay, so that's power in R2. Piv and Ver practice, parallel series practice. Keep on practicing. Let's stop there.